now we are going to start with the third step of metallurgy, that is the reduction. So what we'll be doing in reduction, we'll be converting till now we have done the two steps. We have already converted the raw ore into the concentrated ore. In the second step we have converted the ore into metal oxide. Now we are at third step where we need to reduce the metal oxide. That means we need to convert metal oxide into metal and oxygen. That means we need to separate them, right? Because this is what we are doing, we are doing this process, metallurgical process, in order to obtain the metal, right? So that means this step is a crucial step, because in this step we are going to get the metal, right? So this is our reactivity series, and you will be I just want to make you know that actually this reduction actually depends upon the reactivity of the metals. Like which method is to be choose or which method not to be choose just depend upon the reactivity. So we have three kind of reduction methods. First is by heating, second is smelting, and third is electrolytic reduction. So we employ these three methods to separate oxygen and metal. And what are those three methods? By heating, smelting and electrolytic reduction. So out of these methods, which method is to be choose or which method is not to be opted depends upon the reactivity series. As you all know that we have the reactivity series in which the metals are arranged according to their decreasing reactivities. Like these are the highly reactive metals, these are the moderately reactive metals, and these are the least reactive metals. So accordingly we will be selecting a method whether we have to reduce it with heating or smelting or electrolytic reduction. We'll look for its reactivity, or you can say a place in the reactivity series, and then we will be selecting a method. So let's start one by one. So let us say if I need to separate gold and platinum, how I'm going to reduce gold and platinum, how I'm going to reduce gold and platinum. So the one major thing is that you know that it is least reactive. So when they occur in nature, they do not occur in a combined state, they occur in a free state. Although many metals, almost all the metals, they occur in a combined state, but it is an exception that gold and platinum do not occur in a combined state, because they are very, very, very less reactive. So they occur in a free state. So whenever they occur, obviously they are not combining with anything, so you can use it as you can say a crude metal, right? So that means you don't need to reduce them. But if we talk about these metals, like the metals which are present above it, like copper, mercury and silver, we can do it by heating. We can do it by heating. So as you can see that they are very less reactive, almost means I'll not use the word least reactive, they are less reactive, right? So that means the bond between oxygen and the metal is not so strong. So we can easily cleave that bond by heating. So let's see that how. Suppose I have a cinnabar ore. This is my cinnabar, HGS, ore of mercury. So what I can do it, first in the second step I'll be roasting it, because it is a sulfide ore, heating in presence of air, and what do we get? We get HgO and SO2. And then, so this is the second step. Now in the third step what we do, we just supply it with air, or we just heat it, and after heating what we get, mercury and oxygen get separated. Because it is not so reactive, so that means the bond between mercury and oxygen is not so strong. So we can easily cleave it by heating. This is what I have done. I have supplied it with heat, the bond actually breaks, and this separates out, right? Likewise we can do it for the sulfur also, copper also. Let's say it is a ore of copper, that is copper glance. This is my copper glance ore. As you can see that it is a sulfide ore, so that means second step, for all sulfide ores, what we do in order to convert or in order to oxidize them, we roast them. So likewise I am roasting it, heating in presence of air, and what do I get? I get the oxide and sulfur dioxide. Now this copper oxide can be reduced by heating. So I just simply heat it, because it is not too strong, the bond is not too strong, they will cleave and the metal gets separated. So that means the metals which are not so reactive, I am not talking of the least reactive, I am talking of the metals which are present above gold and platinum, means they are below hydrogen but above gold and platinum. So they can be reduced by this process, that is heating, right. Second is smelting. We opt smelting method for which metals now? Do you have any idea? We opt this method for moderately reactive metals. We opt this method for moderately reactive metals. So the first thing is that you should know what actually is the smelting. Smelting is extracting metal in fused state, or you can say in a molten state. So in this we will be extracting a metal, obviously we will be extracting a metal from metal oxide, but we will be obtaining it in a fused state, right. So this is what is the smelting, and for this what we need is we make use of reducing agent. We make use of reducing agent, and when we mix them with reducing agent we need to supply it with even with high temperature. Now the question is that which kind of reducing agent we will be using in order to extract metal in a fused state, right. So those reducing agent can be carbon or carbon monoxide, can be aluminium hydrogen, or it can be an auto reduction also process. The smelting can be an auto reduction process also. So let us see that which reducing agents are opted for which metals. So let us say that we have tin oxide. Tin oxide can be reduced with carbon. So here is my tin, that is one of the member of moderately reactive. I can reduce it with carbon, and from where do I get this carbon? This carbon is actually a pure form of carbon, that is like coke, charcoal. So wherever, like in any form in which you get the pure form of carbon, you can use that that form here to reduce. So what do you get? Tin gets separate out and we get carbon monoxide, right. It can be a dioxide also, just depend upon the oxygen content, right. So what happens? Tin oxide combines with carbon, gets reduced to tin, tin oxide gets reduced to tin, and this is the carbon monoxide. Next we have is aluminium and hydrogen. So you know that it's a very important reaction, and the reduction which occurs in presence of aluminium, the process is called as aluminothermy. Process is called as aluminothermy. For example, I have a reaction in which I have an iron ore and I am trying it to reduce with the help of aluminium. So what happens as a result? Iron plus Al2O3. Iron gets reduced and aluminium gets oxidized. This is what a reducing agent do. It reduces the other and itself gets oxidized. So this is what aluminium is trying to do here. You know that there is a special name for this reaction. This reaction is called as Thermite reaction, and it solve a, you can say, useful purpose. It is used for thermal welding. It is used for welding of railway tracks. This reaction is actually employed for the welding of railway tracks. So this is called as thermite reaction. So if somebody is going to ask you about thermite reaction, you need to write a reaction in which the aluminium is just trying to reduce the iron oxide, and you will also write the use also, that is used for welding of railway tracks. But if somebody is going to ask you about aluminothermy, then you need to write that the reduction which is occurring in the presence of reducing agent aluminium, that comes under aluminothermy. So it is an application of aluminothermy, this thermite reaction. Auto reduction. For example, I have copper ore, let us say copper glance. It is a sulfide ore. So in second step I will be roasting it, heating it in supply of air. What do I get? I get this thing. So now I can reduce this copper oxide by two methods. Either I can heat it, right, or I can react with the partially oxidize its own ore. Right. So in both of the steps what we'll get a pure copper, and here also we'll get, but here the gas will be SO2. The copper obtained by this process is something called as blistered copper. It is called as blistered copper. Now what is the reason that it is called as blistered copper? Because it has possessed the holes. It actually possessed the holes. So this is what is the blistered copper. So I think you got it, that we can opt for the process smelting for which kind of metals? The metals which are moderately reactive, neither too reactive, neither less reactive, they are moderately reactive. So we can do it by this method. Third is electrolytic reduction. And you know that this method is employed for highly reactive metals. It is employed for highly reactive metals. So let us see that how this electrolytic reduction take place. So let me draw first electrolytic tank or a cell. So this is my electrolytic cell in which I have a carbon lining. I have just lined it with the help of carbon. So this is my carbon lining, and this lining is going to serve as cathode. Right. Now what do I have in it? I have the electrodes. Electrodes made up of carbon. And you know that which form of carbon is used? Graphite is used because it is a good conductor, right? So these electrodes are connected to each other by means of wire, and they serve as anode, and they are connected by means of battery. So this is the connection. Now you know that now we have electrolytic cell, we have the cathode and anode. So what is left? Obviously we are left with electrolyte. So let's say this is our electrolyte. So let's take an example of aluminium to explain this. So let's say that our electrolyte is alumina, that is Al2O3. Now you know that when we are carrying out electrolysis of alumina or some other electrolyte also, we add certain substances to it. Like in case of alumina, we add two substances, Na3Al(F6) and CaF2. This is cryolite and this is feldspar. This is cryolite and this is feldspar. You know that what is the reason that I am adding these substances? These substances actually lower the melting point of alumina, melting point of alumina, or you can say they just increase the conductivity, because here what we need is a conductivity, that the electrolyte should be able to conduct electricity, because more it will conduct electricity, more it will get dissociated into ions. This is what we need in the electrolysis, right? So this is what is happening, and this cryolite and this feldspar is making the conductivity more by you can say decreasing the melting point of alumina. Now what the reactions are going to take place? So when we will pass a current, this alumina will break up into ions. This alumina will break up into ions, and as we know that we have positive and negative electrodes, so these ions will travel to the oppositely charged electrodes. It is 3 positive, it will travel to cathode. It is negative, it will travel to anode, and respective reactions take place. So let's do the reactions first. So reaction at cathode, obviously 3 positive is travelling here, Al3 positive, that means it has lost its 3 electrons. So we need to convert it into pure metal, and when we need to convert it into pure metal, we have to supply it with the electrons which it has lost earlier. So how many electrons it has lost earlier? 3. So we need to supply 3 electrons back, and this is the pure aluminium. And you know that these reactions continue, and this aluminium start getting deposited on this carbon lining, because always the pure substance is obtained at cathode. Now what happened to this O2 negative? This O2 negative is negatively charged, so obviously it will move toward anode. It will move towards anode. So it has gained 2 electrons, we need to convert it into atom or a molecular form, so that means we need to extract this much of electrons from it. So this is what I am trying to do. I am just extracting 2 electrons which it has gained earlier, and after losing it will again form O. We know that O is diatomic, so 2 oxygen will combine to form O2. And also we know that the electrodes are formed of carbon, and carbon has a great affinity for oxygen. So we will have carbon dioxide gas also. So this is what is the reduction. So what at the end of this you got? Earlier it was alumina Al2O3, and after the reaction what had happened, it gets reduced to aluminium. This is what we were looking for, right? We opted for this third step only to have the metal from the metal oxide. So we are successful. So because we have already reduced the metal oxides by taking into consideration their reactivities and opting specific methods for that, that is by heating, by smelting and by electrolytic reduction. So this is what you can do it, and this auto reduction method is something important, so just keep in mind. So just try it out 2-3 examples like I did for copper sulfide, you try it for another example also, right. So this is a third step. So after the completion of third step, we have reached to a point where we have achieved our metal, but that metal is not a pure metal. We'll say, I'll use a word that it is a crude metal. That means it has certain kind of impurities. So we need to remove that impurities, because when you are using any metal article, what you want, like if I want to have an iron rod, I'm not going to dig any rock or something or have an iron rod from there. What I'll do, I'll go to a shopkeeper and I'll ask for the iron rod, and that shopkeeper will bring from certain factory, and that factory will bring from the certain plant where these metallurgical processes has been carried out. So that means, like if we need certain metal article, we need it in a ready to use form, or you can say we need it in a pure form, right. So this is what is that we need to carry out the fourth step, which is very important and a crucial step, because in that step we are going to get the pure metal free from all the impurities, and even it will be converted into some usable form in which you can bring and use it for your desired use, right. So we'll be carrying out the fourth step now.